thank you for the Elastic community for giving me this opportunity to present our expertise in scaling Elasticsearch at PayPal. So a short agenda here. First, I'm going to be talking about the challenges that we had, and then what we were trying to solve, just to give a summary, because the challenges are multiple slides. So I just want to summarize it in saying what we are trying to solve. And then about the architecture, the version 1 of the architecture, and then the improvements, the hardware configuration and the optimizations that we did, and the revised architecture. And finally, what did we achieve? Okay. So first thing is about the data volume. So in PayPal, normally what happens is we have this habit of getting ourselves ready for holiday traffic. Thanksgiving and Cyber Monday is one of the busiest days for us, and we get significantly like 3 to 4 times higher traffic than normal traffic. In 2019, the graph on the left shows you normally we get around 30K messages from the payment pools to the Kafka topic. This is 30K messages, 30,000 messages per minute, per second. 30,000 messages per second is the inflow on a normal day. And during holiday, like the Thanksgiving and Cyber Monday, as I said, it will be around 140K per second. This was the pattern until 2019. The slide on the right that you see here is the pattern started changing from March 2020. The pattern started changing because of the COVID situation. From March itself, we started seeing increase in traffic volume, and it was going around 180K messages per second. And the peak traffic that we saw that here was on the Thanksgiving day, which was around 400K messages per second, where I'll show you in the last slide about that. So similarly, this is regarding the messages that is getting pushed into the Kafka topic. And similarly, the data that got persisted, the storage size started increasing. And it used to be around 10 terabytes. And now, as of today, we are ingesting around 15 terabytes of data per day. This is the challenge that we had in terms of traffic and volume. The next challenge is so on one side the traffic increases, so we need more hardware, and either we do horizontal scaling or vertical scaling to handle those increase in volume. The problem was horizontal scaling, you need more hardware. Procuring hardware is a 3 months process normally, but with COVID situation it was around 6 months, so it was not easy for us to procure hardware easily. And one more thing is the size of the cluster. The cluster was already a huge cluster where we were running around 224 data nodes and 9 client nodes and 3 master nodes. So simply adding nodes is not going to be a solution. And in terms of vertical scaling, if you look at each bare metal, these are all like monster SKUs where there are around 503 GB of RAM, 64 CPUs, and 21 terabytes of storage space. On each bare metal, we run around 5 Elasticsearch processes. So each bare metal has 5 Elasticsearch nodes, and each of those Elasticsearch node uses 11 processes. So we utilize around 55 processes, and we leave the remaining 9 processes for OS and other activities. And one more challenge we had was like there was a PayPal and eBay used to be together as a eBay Inc. There was a split in 2015, because of which new data centers were set up by PayPal. In those new data centers, some of the AZs, even though it's a single AZ, because of this split, the bare metals got provisioned. The bare metals were getting provisioned in the new data center. Like for example, if you have one AZ1 as an availability zone, that availability zone was split across multiple data centers. One was in Salt Lake City, another one was in Bluffdale. These are all like not visible to the developers. We just ask for capacity and we just get the additional capacity, but we don't go into the details of which data center it is provisioned and things like that. So that was one more challenge. We deciphered all these things later. So we fixed them in our new setup. Uh, let me know if you guys have any questions, or if I'm fast, or if you have any difficulty in understanding what I'm talking or anything like that.
I have a question. Hi, this is Shubha here. I actually work at Elastic. I have a question around if you can talk a little bit about why PayPal like choose to be self-managed instead of on the cloud. Like you did mention that provisioning the infrastructure is a significant load.
Okay. So your question is why not Elastic Cloud? Why on-premises choice?
Yeah.
Yeah. So primarily, Elastic data is PayPal data is very secure data. We cannot go on public cloud as is. So, and we were also exploring options of having Elastic Cloud on-premises Elastic Cloud deployments, but due to licensing cost, it was pretty expensive. And we already had the setup, and we already had the hardware. Though acquiring more hardware was difficult in shorter time, it is always a challenge to acquire hardware and scale it on a need basis. Cloud is really flexible, but due to security and other reasons, PayPal data cannot be moved to cloud easily.
Got it. Thank you so much.
Yeah, no problem. So another problem that we had with the hardware was these clusters were there for like almost 6-7 years. So each time we get the hardware, they all had different hardware configurations. So one is the SKU will be different. The way it was configured was different. So we did earlier when we start doing as a developer, you don't pay attention to all these things. We assume things are similar, but eventually when you run into issues, that's when you start looking into these kind of things. So whenever you have huge clusters running, you it's always better to focus right from the hardware level to understand whether they are all having a similar setup. So if you see here on the left side, we had 6 disks, with 3.5 terabyte each, and they were all like independent mounts. When I say 6 data mounts here, it means like if you see here, the device is set up that each disk is a separate mount point. So these multiple mount points will be configured in the path.data of the configuration file in Elasticsearch. So this is dependent on this way of configuring hardware is dependent on ES for data striping. So when you write data into an index, Elastic takes care of striping it on multiple disks. Whereas on the other side, if you see here, the number of disks were less, like only 4 disks with 2.5 terabyte of data each, and one is 3.5 terabyte of data each. And the last one is we did have some bare metals that was configured for RAID 1.0 instead of RAID 0. So all these hardware configurations do matter. So the configuration and the optimization that we are talking about is not important always. But when you're talking in terms of scale, like when you just spin up a 3-node Elastic cluster and run with a small number of ingestion and search queries, these things will never be a problem. And all the defaults, JVM settings and Elastic settings will work absolutely fine with even a VM or a bare metal with RAID 0 or RAID 1.0 or Nutanix or any environment is fine. But all these things matter when we go in scale, like ingesting 15 terabytes of data per day with around 400K messages per second. When things come in that scale, that is when each and every thing matters, inclusive of CPU cycles. So moving on from hardware challenges to the Elastic side, again, like as Rich mentioned, Elastic version definitely makes a difference. So we were running the cluster on 5.65, 5.6.5, and we were planning to move it to 6.8.3, which was the most recent tested production version on our side. Most of our clusters were running on 6.8.3, so we wanted to move this payments monitoring cluster also to that 6.8.3. But always the challenge, the issue with the upgrades is like dual capacity, and then the breaking changes, all the normal things that that apply in any Elastic version upgrade came into picture. We did run into some issues. I'll I'll cover it in the subsequent slides. Then because of this volume, the cluster was not able to handle the pressure. So there was a very high memory pressure that was causing mainly three problems that you can look here. One is like out of memory, and the other one is nodes will keep disconnecting. They will not respond in time, and so that the master thinks the node is not alive and it will remove it from the cluster. And again, then the node will respond. There will be a delayed response, and then again the master will add it back. So this cluster stability was a big concern. One more thing that we had enabled was dynamic mapping. The dynamic mapping was set to true. This is because like the logs are pumped in from different payment services. So we didn't want to really define a mapping initially. We gave it flexible to the user, like whatever fields they pass in a field called payload. We were just breaking that. We were string tokenizing it based on equal to, and then taking them as a key value pair. We just were indexing that. But that actually gave us a very hard time when we were going at scale. The default limit is 1,000 fields per index, is what Elastic allows us to do, but we can increase that limit. We did increase the limit, but we were always hitting the buffer of like 5,000, 6,000 fields. And anytime there is a change in that field, the data has to be propagated across all nodes, and that was causing delay in all the nodes acknowledging the change. And that was those things were impacting the ingestion and performance as well. So as you see here, we had a very hard time to, with those kind of setup, we had a tough time to push the ingestion rate beyond 9 million per minute. So the maximum was around 9.2 million per minute was the ingestion rate that we could achieve with that kind of setup. This is a previous setup that we had. So the graph on the right shows the lag. When the ingestion rate goes down, you see the lag increasing. Normally, it'll for a 30-minute period, the lag, if we don't consume it at a good rate, the lag will build up to like 200 to 300 million easily in 30 minutes. So this is the architecture that we had originally. So here on the left side, you see all the PayPal applications that writes logs into a component called CAL. The CAL is nothing but it's a centralized application logging. So this component takes care of pushing the data into a Kafka topic, and we consume from Kafka topic and ingest into Elasticsearch. So the ES proxy layer here reads from the Kafka topic and it ingests into Elasticsearch. On the other end, developers and the payment monitoring team, they have dashboards to monitor the payment transactions that is happening every day, and they closely monitor that to see if there is any dip in transactions or increase in transactions and act accordingly. So on the other side, the developers use the Kibana tool to triage any issue using the log details. So they also use the same proxy layer, and it goes to the client nodes. The client nodes take both searches and ingest and respond accordingly. So here I've specifically highlighted these things like the Kafka partitions, how many partitions we had. Initially, we had only 60 partitions and 30 consumers. So the consumers were sharing partitions, like 2 partitions per consumer. And then I've mentioned the size of the cluster here, like we had around 224 data nodes. And here I have mentioned that problem where it was only one AZ, but the hosts used to be in 2 different data center locations. These kind of things definitely impact the availability of the cluster, because the network comes into play here. Any calls for the nodes to acknowledge, there is a network latency involved here that impacts the cluster availability. So then just have highlighted some of the features that are there in the proxy layer. We have something called query optimization. Query optimizer. So in Kibana, normally people use something like a wildcard index pattern like cal star or cal dash mmddyy star or things like that. So instead of giving a specific index, they create the index pattern and they do the wildcard search. So what we do internally in the optimizer is, if you are searching for last 15 minutes, we know it is, we have in our system, we had daily indices for this particular payments pool. So if it's the last 15 minutes, we narrow down the query to just that 1 day index. If the window is across 2 days, then we just use 2 days of index. We restrict the searches to just those two indices, which is 1 index per day. We have around 14 days of retention, so we maintain 14 indices in this cluster. And anytime the query comes, we use this query optimizer to see how many indices this query should span across. So that's what we do with the query optimizer. And this ES proxy also has this a very good feature of blocking the queries. All expensive queries, we just get that pattern and then we block it. Of course, first time it's definitely a hit. We learn from the mistake, and then we just block it so that we don't repeat the mistake. Then also this proxy is used for DR switches, like when a primary cluster is in a trouble, we route the calls to the secondary cluster, which is nothing but a disaster recovery cluster. This is about our architecture that we had. This is V1. We made minor tweaks here that made a good difference, which I'll share it in the subsequent slide. Any questions, or can I move on?
One question.
Sure.
Do you do force merge on your daily indexes to optimize? Okay.
No, we didn't do any of those because of the very high ingestion rate. Doing any of those operations were bringing the cluster down. We did try doing force merge while this kind of ingestion is going on into the cluster, but it was impacting the cluster. We had cluster availability issues when we tried to do the force merge.
Okay, thanks.
So even we tried this hot and cold architecture where we were moving the data of older indices into a lesser expensive machines and stuff. We did try those things. Any such moments were causing problem. So that's why we left this. You will see my revised architecture where we had bare metals just taking the ingestion and the search queries. We were not loading this cluster with any other activity.
There was a question in the chat. Is this being used as a primary data store?
So this is just for triaging and monitoring dashboards. So the data is like log data. So yes, the answer to the question is yes, it is the primary data store for just these logs. Of course, the logs are available in another system called the centralized application logging, but for our search and monitoring dashboards is built on this data, this logs data.
Okay. Also, I had a question. The query optimizer, I think Kibana or Elasticsearch, and maybe it didn't come along until some later version. I think it already knows which shards have the data when you do a query for like the last 15 minutes. I don't know, maybe this is something more recent than the version you're running. I don't think you need to do that part yourself anymore.
Oh, and until until at least 5.6.5, we did not have that available. So we did have to actually even 6.8.3. I do see that when you use the cat star pattern, I mean the star index pattern, it spawns across all the shards in the index. It doesn't restrict it to just 1 day index. Maybe I'll sync up with you offline to see if there is anything that needs to be changed in the configuration.
Very good.
A question on ES proxy. Sorry, just a quick question on ES proxy. Is that something that you guys build homegrown? And how do you put that between the Elasticsearch cluster and Kibana? Because as far as I'm aware, Kibana directly talks to Elasticsearch.
So it is a URL that you define in the Kibana configuration file, right? That URL, we just point it to a VIP. That VIP is nothing but our ES proxy.
Oh, okay, got it.
So sorry about that question about whether this is used as a primary data store. The logs are actually persisted in the centralized application logs also, and this is a secondary store where this is used for searches and dashboards. Okay, moving on to the next slide. So just to summarize all that we were trying to solve, one is the memory pressure. And because of this memory pressure, we were having delayed response from nodes. To handle that and have the cluster available, our support team was always monitoring the dashboards and log files, master log files, to see if there is any delayed response from any of the node, and they were restarting that node to keep the cluster alive and serve the traffic without any interruption. So that was around 40 to 50 node restarts per day was the kind of effort that was involved to keep this cluster stable. And then, as I said, we want to boost the ingestion rate so that the lag comes down quickly. So we are able to consume fast, and the real-time data is available for developers and the monitoring folks. Then another problem is anytime there is an issue with the cluster and your lag builds up. As I said, like in 30 minutes, the lag will be around 200 million or so. So if the lag goes over 1 billion, then this previous version of the cluster was taking several days to catch up with that lag. It used to be like 2 to 3 days for 1.5 billion lag in consumption. Okay, so the first optimization that we did was standardizing the hardware. The current cluster that we built, the hardware is all like it's not any it's no more hybrid, and it's all like a homogeneous cluster where all the bare metals are of the same type. So the best part of this one is these bare metals come with two internal SSDs, which are like 256 GB each. So we configured the OS in these smaller SSD drives, and it is configured as RAID 1.0. So even if we lose one disk, we are still able to bring back this bare metal and access the data and continue with serving traffic. And parallelly, somebody will be fixing the one that went down. So that's the advantage of configuring it as RAID 1.0 and having the OS installed on these internal SSDs. Then the RAM is around 503 GB, and we have 64 vCPUs. The key thing is the way how we configured the data disks. So earlier I mentioned about having individual mount point for each of the disks. Instead of that, we combined all the 6 disks into one logical volume, and we had only one mount point called /xes data. Under this /xes data, we will do 5 installation of Elasticsearch, and we'll be running 5 Elasticsearch processes. Now what happens is instead of depending on Elasticsearch for striping, the data striping is done by the OS itself, and this seemed to improve our performance really well. So this is about our hardware setup that we chose for the cluster. When you do use these internal SSDs, one thing that you need to focus on is we have to have FSTab entries with UUID. Otherwise, what happens is sometimes that when the hardware boots up, it swaps the disks that we have for data with the boot, and it doesn't come up at all. The hardware will not boot at all. So it is a must that we define the FSTab entries with UUID for each of this storage device so that we don't run into that issue. Okay, moving on to the next slide. Coming to Elasticsearch and Kafka for optimizations. The Elasticsearch, as I mentioned, we upgraded from 5.6.5 to 6.8.3. We did face some breaking changes like the Boolean type in 5.6, and the previous versions allowed for any value in Boolean data type. It's not narrowed down to just true or false. So in starting 6, it is just true or false. We cannot have any other data values in a Boolean field. So that did hit us, and we had to make some modifications to get that working. Then, as I said, we had issues with dynamic mapping. We just disabled that and defined static index mapping. And the key thing is we separated the client nodes from search and ingest. Like we had dedicated search and ingest nodes. This way, what happens is when there is a problem with the cluster, when you get a bad query and the cluster is in a bad shape, we can block just the search node, search client nodes. We can just bring down the search client nodes so that the searches does not happen and the ingest continues. So this is really flexible to have dedicated nodes for searches and ingest. And the other issue that I talked about, say a cluster nodes getting deployed across multiple data centers. So the key thing that developers should understand here is when we get a hardware, it is just not like, we should not assume things like they are all in the same data center, they are all of the same configuration and stuff. So it's our responsibility to dig through these things and make sure that they are all the same nature and it is what we expected it to be. And the interesting part is the JVM tuning. We have spent several hours here and we can keep going hours and hours here. And these things really matter when you want to save even one CPU cycle to squeeze out some more performance from the hardware and from the cluster. Like the best thing that we did was we have a different kind of configuration depending upon the node type, the Elastic node type. For the master and the client nodes, we have configured the max heap as 30 gigabytes. And out of the 30 gigabytes, the new gen is 10 gigabytes and the old gen takes 20 gigabytes. This is the setup that we have for master and client nodes, and data nodes, just that the new gen size is reduced to 6G. You will see why. I'll just give you some more details on why we chose 30 gigs and why not 32 gigs. There are articles in the internet, and even Elastic talks about that. It's mainly like there is something called compressed object pointers that comes into play when you go beyond 4 GB of heap size. So I can show you here. Let me know if you are able to see the screen. I'm sharing it. Okay. So if you see here, when you use 31 gigs, the compressed object pointer comes into picture, but they use something called non-zero based. It's a compressed object pointers, but it is non-zero based. What it means is there are 32 bits is used for storing the memory address, and with 32 bits you can go only up to 4 GB. In order to go higher heap configuration, the compressed object pointers is used by JVM, and it had additional 3 bits. And those 3 bits makes it like 2 to the power of 35, with which you will be able to go up to 32 GB. But when you go that way, there are 2 modes. One is zero-based reference, other one is non-zero-based reference. The difference between the zero-based reference and non-zero-based reference is this. So when you're using just zero-based reference, in order to resolve the memory address from the way it is stored, JVM has to do just a left shift operation by 3 bits. And similarly, decoding and encoding happens. The decoding and encoding operation happens by just left shift and right shift of the bits, 3 bits. This is a very fast operation, but when it is non-zero based, this if logic comes into place, and this if logic has to check whether a particular address is null, and also it has an add operation to the base value. So one CPU cycle operation becomes 3 CPU cycle operations in this non-zero based references. So that is why we have to make sure that we have non-zero, we have zero-based reference in the setup. And this is not standard across all the bare metals. We can never say the setting in one server works in the same way as in the other server. Like for example, if you see in our production servers, by bringing this down to 30 GB, we were able to bring it down to zero-based references. But in my local laptop, if I try, I had to come down up to 27 gigs to make it zero-based reference. Until then, it was non-zero-based reference. Hope it was clear. So we use the specific Java commands like unlock diagnostic VM operations and use compressed ops to do this kind of check. Any questions on that? Okay, I take that as no. So then another thing that we did was on the Kafka side, initially we had 60 partitions taking the log messages. We increased the partitions to 100. And we also, what we did was we made sure that there is no sharing of partition by consumers. So we made sure like every partition has only one consumer, and that consumer is dedicated to that partition to boost the scale, volume of transaction messages that it can read and ingest into the cluster. Okay, so this is the revised architecture. So the changes that we made was one at the hardware level, where we configured the machines to be RAID 0 with the OS installed as a RAID 1.0 in flash in the internal SSDs, and the data partitions as RAID 0. And next at the Kafka layer, where we increase the number of partitions and we increase the number of consumers, and we made sure that it's 1:1. And also the change that you can see here is that the ingest client nodes are separate from the search client nodes. So the searches are just routed to this search client nodes, whereas the ingest goes to the ingest client nodes. We also added a little more data nodes here. So from 224, the data node count was brought to 240, and the client nodes were also increased to 11 client nodes, as we were using for dedicated ingest and search. So we happened to increase the number of client nodes also. Everything else remains the same from V1 architecture. Any question on this? Okay. So with the new setup and those JVM tuning and the hardware configurations and stuff, we were able to see the results. The key accomplishments are shown here. So on the Thanksgiving Day, we had around 400K messages per second. So this cluster was able to consume that in a very smooth way. So you will be able to see here, we were able to hit around 20 million ingestions per minute. And the heap always remained below 75%. Maybe one or two nodes were like 76 or 77, but on the whole, the entire system was always, the entire system is always healthy, and we don't have any more memory issues. And if at all we have any incident, and if we were to catch up with the lag, we are able to consume around 1.5 billion lag in just 3.5 hours, which used to be like 2 or 3 days earlier with the older kind of setup. That's pretty much what I have.
We do have a couple questions that came up in the chat. One was what type of collections are you using for the logs? Is a Logstash involved, or is it just Kafka right to the cluster itself, or what's the? So
the Scal is a proprietary component that is developed by us, and that Cal component is embedded into each of the application. So the application, when they have to write log, they just use this cal component and write it to the log files. And this cal component itself takes care of publishing those log messages into Kafka. It's a Java application that takes care of posting the data into Kafka.
Okay. And then another question is, how long did it take you to get the memory right?
So if I understand the question right, for
yeah, how long? How long do you to optimize that?
So earlier we didn't know about this compressed object pointers. We thought like using 31 gigs or 31 gigs will be ideal, and we started using it. These are like we spent several hours to research and understand this. I would say at least close to a month to bring all these in pictures. Like anytime you do this change with the live traffic, we want to get the metrics and make sure that we are not impacting the traffic and things like that. So changes took some time. At least I would say a month was spent on all these JVM changes.
Did you deploy like one data node at a time, or like did you like one master? Did you kind of roll this out gradually?
Yes, initially when we were doing it, so master and client nodes were easy because we just the original setup had a very less number. Master is only 3 anytime. Just the client nodes were very less. The data nodes were a little more complex to deal with because of the number of nodes. So yes, to answer your question, we just tried it with few nodes. We always see the dash. We have something called a metric monitor to collect the node stats and check the health of the cluster. So we use those dashboards heavily to tune this JVM.
Okay. And another question is, do you ever use the Percolator API for anything? Okay.
No.
Oh, there was another question up above. Do you have multiple Kibana instances?
Yes, 3 Kibana instances.
Right. Any other questions? Let's see. I'm reading another question that's coming through right now. So Forrest has asked a question about version 7, lots of using the different ingest nodes versus coordinated nodes. And so far he hasn't found any different URLs for the different nodes. I haven't done anything coordinated nodes since version 6, and I'm starting to work with version 7 now. But it's a small, I'm just in POC mode and doing some testing, so I haven't run into that yet. So has anyone else using version 7 and anyone who could chime in and help with that question?
Yeah, this is Sachin. I use version 7.13, and we use a coordinating only node for Kibana. So wherever the Kibana instance is running, we use coordinating only node.
So you have to install that as along with Kibana on the same node?
Yes.
Okay. Yeah, that makes sense.
Sorry, yeah, I think my question's more around the Elastic Cloud stuff. I know it's kind of separate from what he was pointing out, but I just wanted to imitate how he was doing the ingest nodes and the search nodes, and like being able to set that up in the Elastic Cloud product. Like they don't like give you an easy way to say, oh, here are the URLs for this and here are the URLs for this. It's always just, here's this one URL.
Yeah, I think that's kind of one of the challenges with the cloud itself, because you can't do as much as you could as if you're running your own cluster.
Gotcha.
Yeah, with us also it was flexible because of the proxy layer that we use. So at the proxy layer level, we kind of take these controls.
Cool, thanks. Good talk.
Yeah, just one more thing that I wanted to share is again, never let the a new gen size by default. Like normally, all JVM documentation, everything talks in terms of a new ratio, which is like 1:2. So if you have 30 gigs, and then it should be 1:2 ratio, in the sense 20 gigs goes to old gen and 10 gigs goes to new gen. But it doesn't happen that way at all. And there are multiple articles in internet why it doesn't happen that way. It is basically because of this ergonomics of JVM. There is a computation that I am highlighting here, which comes into picture. So it takes a minimum of this formula here, which is comparing the new ratio, and it compares it with this scale forward on engine per worker and that times parallel GC threads. Always this becomes very low, and because of this, even in 30 GB, only 1 GB or 2 GB goes to new gen, and that is again divided by 1/8 for Survivor and Eden. Which is again, it will bring down the Survivor space to around 100 MB or 150 MB. That is one more thing that we should keep in mind. Those JVM settings will work when the scale is not a concern. So I have some examples here where I have shown that if you see here, I'm using 30 gigs, but the new size will be like very less when compared to the old size. This is around like just 1 GB, and this is around 31 gigs, sorry, 29 gigs. This is something that we should keep in mind.